All right, here we go. The recording is starting, so let's finish this SI sheet. So to start, we need to name the carboxylic derivatives. I did a more detailed video on how to do that, or it's in one of my previous videos, so I'm going to go a little quicker here. So first step, name the longest carbon chain coming off of the carboxylic acid derivative. So here, the longest carbon chain is 7 carbons. If you remember, 7 is hept. We have an alkene on carbon 3, so we'll indicate 3-ene. And then we're not going to end it in the ene because it's a carboxylic acid derivative. More specifically, it's an amide, so we're going to end it in amide. Like that. So now we got to add the substituents coming off of the amide nitrogen. So let's number how many. We have 2 ethyl groups. So 2 ethyl groups can be written as diethyl. So that's how we're going to write it in the name. Diethyl. And then to indicate its location, instead of doing numbers when it comes off of the carbon chain, we're just going to do 2 N's to indicate it's coming off of the nitrogens. And then the last order of business is we have an alkene. We have to identify if it's E or Z, and this is E, since both priority groups are on opposite sides of each other. So then we're going to list it as E. So that's the full name. E and then diethyl hept3 amide. Next one, same process. First number the longest carbon chain. So 3. Let me do it over here. 3, if you remember, is prop. And then we don't have any alkenes or alkynes, so propan. And then because it's an ester, we're going to end it in O8. So that's the ending. Now we have to indicate how many carbons are coming off, or we need to indicate the substituent that's coming off of the ester oxygen. So there's 4. If you remember, 4 is but. And we're just going to name it as butyl, because that's how you name the carbon chain coming off of the ester oxygen, end it in YL. So butyl propanate. All right, next one, acid chloride. Let me zoom out a little bit more. There we go. Acid chloride, once again, we're going to number the longest carbon chain, which happens to be 8. 8, if you remember, is oct. So we're going to put an oct. No alkenes or alkynes, so octan. And then because it's an acid chloride, the carbon chain is going to be ended in OYL, followed by chloride to indicate it's an acid chloride. Next, we need to add the substituents. We have a methyl on carbon 3, and we have a bromine also on carbon 3. So we can include that in the name alphabetically. So methyl would come second, with bromo coming first. And let me move this so I have more space. So 3-methyl, and then 3-bromo. And then the last thing we need to do is, because we have a chiral center, we have to indicate if it's RS. So on our chiral center on carbon 3, bromine, highest atomic number, gets number 1 priority. This carbon on the left, we get number 2 because it has the acid chloride. Then this carbon chain is longer than just a methyl, so that we get 3. And then the methyl gets 4. If you draw from 1 to 2 to 3, it's clockwise, so R. But because our number 4 priority group is on a wedge, we need to flip to give us S. So let me move this over. And our full name is S3-bromo 3-methyl octanyl chloride. Last one, we have a symmetrical anhydride, so that actually makes it easier to name because we can just combine each side of the anhydride into the same part of the name. So first, let's number the carbon chains coming off of them. They both have 4 carbons coming off of them, so 4 is but. No alkenes or alkynes, so butan. And then the way you name the carbon chain or finish the name of the carbon chain coming off the anhydride is OH. And then you finish it with space anhydride. So that would be the full name of that. Butanoic anhydride. All right, the next part. First, I wanted you to fill out the carboxylic derivative ladder, and you'll see why. We're going to use that for the part on the right. So first, if you notice about the carboxylic acid ladder, it's arranged with, most reactive on top with least reactive on bottom. So if you remember, the most reactive is going to be the acid chloride, so we can put that on top. And I'm not going to show it in this video, but normally the way you determine how reactive these derivatives are is to draw the zwitterion. So if you're still trying to figure out what's reactive, what's not very reactive, draw the zwitterion. After acid chloride, the next is the anhydride. So we'll draw in the anhydride. And then following the anhydride, we have two carboxylic acid derivatives that have pretty similar reactivity. So I grouped them just equally. And that is the ester and just the carboxylic acid. Those are going to have pretty similar reactivity. And then the least reactive is the one remaining, which is the amide. Oop, come on, draw a better end. There we go. So that's the ladder, and we're going to use that on the right here, and I'll show you why. So let's see what we need to convert. We need to start with an acid chloride and go to an ester. If we look on the ladder, the acid chloride is at the top, and the ester is right here in the third spot. When you are going down the ladder, you can do that in one step. So this is going down the ladder. And I'm just going to put that can be done in one step. So how do we get from an acid chloride to this ester specifically? Well, let's look at the difference between the two. The only difference between this acid chloride and this ester is that this acid chloride has chlorine, where this has like a methoxy group. So in our reagents, we should have this methoxy group because we need that to attack the carbonyl. So we should have this oxygen attached to a methyl. And because acid chlorides are so reactive, we can just throw a hydrogen on there. And although this alcohol isn't very reactive, because the acid chloride is very reactive, this weak nucleophile can directly attack this very strong electrophile. So that would work out. You could also put NaO methoxide, or you could also give acidic conditions, so throw in sulfuric acid. But just the alcohol would work as well because the acid chloride is so reactive. So that's going down the ladder. Let's look at the next one. Going from an anhydride to an acid chloride. If we look at our ladder, acid chloride is number 2 here, and anhydride is at the top. Or I said that in the wrong order. The anhydride is here at number 2, and the acid chloride is here at the top. This means we are going up the ladder. When you are going up the ladder, you can't do that in one step directly. You need to, it'll be multiple steps. So we can't go directly from an anhydride to an acid chloride. We need to go to something else first. And how do we make acid chlorides? Let's first think about that. There is one reaction we have learned a lot this semester in order to make acid chlorides, and that is thionyl chloride, or also known as Sochel 2. Let me redraw that arrow. And what does Sochel 2 or thionyl chloride react with? It reacts with carboxylic acids. And the carboxylic acid, this is going to be the median in order to go up the ladder. Anytime you are going up the ladder, you need to go through the carboxylic acid. So now we have to figure out how we can get from an anhydride to a carboxylic acid. And the way to do that is we just need to add an OH group on there, and we can get that from water. Because anhydrides are pretty reactive, water will just react with an anhydride. If you were working with something else like an ester or an amide, for example, then this would need to be acidic conditions or basic conditions. But an anhydride will react with just water. So that'll be the first step, is to convert the anhydride to the carboxylic acid. And then following that, we can use thionyl chloride in order to get to our acid chloride. All right, last one, amide to an anhydride. Amide is at the very bottom of the ladder, where the anhydride is the second most reactive. So that means we're going up the ladder, meaning it's also going to be multiple steps. Oh, up the ladder, not up the multiple steps. Oops. So like I said earlier, in order to go up the ladder, we always have to use a carboxylic acid as the median to get up the ladder. So that means we need to convert an amide first to a, let me indicate. For one, we need to convert the amide to a carboxylic acid to start. And how do we convert an amide to a carboxylic acid? Well, we can use water, but because amides are very unreactive, a weak nucleophile isn't going to react with something that is very unreactive. So we need acidic conditions. And then we also need heat because amides are very unreactive. So that takes us to step one. Now we still need to get to the anhydride. We can't go directly carboxylic acid to anhydride because that would be going up the ladder. But in order to get all the way up the ladder, we can do thionyl chloride once again to get to our acid chloride, and from the acid chloride to the anhydride, that'd be going down the ladder, so that would be an easier reaction. So Stockholm 2 or thionyl chloride, and then we can go directly. Let me erase that. We can go directly from a not carboxylic acid. We can go directly from a, why am I blanking on an acid chloride to an anhydride. And the way we do that is, I realize I'm missing a carbon. Let me redraw that arrow then, and then I'm missing a carbon here. I'll fix that on the actual worksheet I sent out. Then to go from the acid chloride to the anhydride, the only difference you'll see between the two is that this has a carbonyl part to it, where this has a chloride. So to remove the chlorine and add this carbonyl part, we're going to need that carbonyl part in the reagents, and it's just going to be a carboxylate. So I'm going to rewrite that as Na plus the carboxylate. So that would take us directly to there. So let me write that here. That is how you go from a acid chloride to that anhydride specifically. And let me change color that. Okay, so that's going up and down the ladder. Now we get some mechanisms. So we're reducing an amide to an amine. If you notice, whenever you're doing mechanisms, if you're stuck, what I recommend is just look at the difference between the starting material and product. And the difference is that instead of having a carbonyl in the product, we have 2 hydrogens. So that means we need to add on 2 hydrogens. And what's our hydrogen source? This is our hydrogen source. So we're going to be using this Li, or lithium aluminum hydride, in order to add on 2 hydrogens to remove the carbonyl. So let's draw out lithium aluminum hydride. It's going to look like this, and let me draw one of those in blue. Aluminum has a negative charge, and then lithium is just chilling out next to it. So if you remember with the lithium aluminum hydride reaction, the hydrogen is going to be what attacks the carbonyl and then push the electrons onto the oxygen. So the result of that step then gives us 1 hydrogen added on and an oxygen with a negative charge. So now we have 1 hydrogen added on. And now the next step is we are going to need this alcohol, or not, that's not an alcohol. We need that oxygen to attack the aluminum hydride that just lost a hydrogen. It's going to attack it. And then next, we get this. Let me write it on the side. And then that aluminum has a negative charge, and we still have that hydrogen that we added on. So we don't want this oxygen group here anymore. So we can kick it out. And the way it's going to be kicked out is that this nitrogen here is going to do resonance in order to push out the oxygen aluminum group. So now we have this group here. Oopsies. Kind of like an imine. And what's separating us from where we are and the product is we need to push this double bond back onto the nitrogen, and we need to add on a hydrogen here. So that's what we're going to do in the last step. We're going to use another version of this lithium aluminum hydride in order to add a second hydrogen onto that carbon and push the electrons. I didn't realize I already had the arrow written. And push the electrons onto the nitrogen. So that gives us the product. All right, next one. Once again, let's look at what's different. In the starting material, we have an ester group or an ether group. And in the product, we have a hydrogen instead. So we need to remove this ether group and add on a hydrogen at the same time. And do we have a proton source? Yes, we have Dibal. Isn't it? It's diisobutyl aluminum hydride. So that's gonna look like this. And then we have a hydrogen here. These are isobutyl groups, so that's why it's di for 2. This is isobutyl because these are isobutyl groups, and then aluminum hydride, which is here. So that's why it's called Dibal H. So in the first step, we are going to have this oxygen attack the aluminum. Because if you look above, you'll see that aluminum can have 4 bonds. But currently, it only has 3. So that allows oxygen to attack aluminum. Because aluminum can have 4 bonds, but currently it only has 3. So let's show the result of that. I'm just gonna, I'll draw them out. Why not? And then we have a hydrogen. All right, so now this oxygen has a positive charge, and this aluminum has a negative charge. So now that we have the Dibal attached, we can have the hydrogen attack. And then that puts that hydrogen on our carbonyl, and then we can get rid of that double bond to get rid of this this positive charge on the oxygen. So let's draw the result of that. So now we have a hydrogen there. Let me just draw it in. And we still have this oxygen attached to this Dibal group. So now let's see where we are and how we can get to the products from here. So we need to reform a carbonyl. We need to get rid of this alumina group, and we need to get rid of the ether group. So that's a lot to do. And this is the end of the first step. Now starts the second step. And what's going to happen first is water is going to come in and attack aluminum to give aluminum its 4th bond. And I'm going off the paper, but that's okay. Hopefully we can still see. Yeah. So now we have this group. And let me actually draw out the hydrogens, and I'll show you why. Now we have this group. It's a lot of, And here, now we're going to go in one step from where we are to the product. And the way that is done, oh, come on, is we're going to do everything that I previously mentioned that separates us, that separated where we were in this step to the product. So we needed, let me get my, there we go. So we need this aluminum to be taken off of this oxygen, and we need a double bond to be formed. So we're going to do that in one step. This oxygen is going to take the electrons from this oxygen aluminum bond and push them to create the double bond right there. And that gives us a carbonyl. The only problem with that is then this carbon is going to have too many bonds if it forms double bonds. So to solve that, it's going to kick off this ether group. And then at the same time, this ether group is going to be protonated by this hydrogen over here and push the electrons onto the oxygen. So a lot of arrows in one step, but that is how you go from this step to the product. All right, next two. Grignard, this methyl with magnesium can be rewritten as this. And let's look at the starting material and the products. So the differences are we no longer have a carbonyl, instead we have an alcohol. And then instead of having a ether group coming off, we have two methyls, and we have two equivalents of two methyls. So this is probably going to be our methyl source. If you remember from the metals chapter, this bond right here is an ionic bond. So we can split that and give this carbon a negative charge and the bromine a positive charge. And with this, we can have this strong nucleophile attack the carbonyl and push the electrons onto the oxygen. And draw the result of that. Now we have one methyl group added, and we have an oxygen negative charge. So we added one of these methyl groups on. We still need to get rid of this ether group and add on another methyl. So first, let's get rid of the ether group, and we need to account for this this negative charge. So what we can do is we can do resonance to reform the double bond and kick off this ether group that I realize is missing a carbon. All right, the result of this then is now we have a ketone. And what's good about having a ketone is that means we have an electrophilic carbon right here. That allows us to use another methyl Grignard to attack that carbonyl carbon, push the electrons onto oxygen. And now we have that second methyl group added on, which we needed to get to the product, of course. And let me draw the result of this. And then what's separating us from where we are in the product is the acid quench. So let's just protonate this oxygen, and that gives us the alcohol and takes us to the product. And let me draw a line, separate these mechanisms. Oops. I'm going to do that quick for this one as well. Oh. All right, last one. I did it again. This is by far the easiest mechanism on this sheet, or at least it's the quickest. So that's nice after a few long ones. All right, so here we have a acid chloride, and we need to convert it to a ketone. And let's number the carbons. So here we have 4 carbons, and on this side, we also have 4 carbons on that side. And then in this Gilman reagent or cuprate, we have 2 carbons. And then, oh, I'm missing a carbon. This should be 3 carbons. So here we have 3 carbons. And then on this side, we also have 3 carbons. So the difference between the acid chloride and the ketone is the acid chloride has a chloride group, and this ketone instead has a propyl group coming off of it. And if we look at a reagent, we have a propyl group here as well. So that's probably what we're going to use in order to add the propyl group onto the acid chloride. Because this is an ionic bond, that means that this carbon really has the electrons in between this bond. So this carbon can then directly attack the carbonyl and push the electrons onto the oxygen. And let's draw the result of that. We have an oxygen with a negative charge, and we just added a propyl group on. And then what's separating us from where we are in the product is we can kick the electrons down from the oxygen to reform the carbonyl. And we don't want this chlorine group in the product anymore, so that can get kicked out. And that would get us to the product. So a nice quick mechanism there. All right, last page. These questions are a little harder. This first question isn't too hard, but I asked kind of an easier question before the harder question comes. So predict the product. We're starting with an anhydride, and we have an alcohol. Anytime you have an anhydride reacting with an alcohol, what's going to happen is one side of the anhydride is going to be taken off, and then this alcohol is going to be added to that carbonyl to create an ester. So if we draw the result of that, we're going to keep one of the carbonyls, going to add on that oxygen, and we have 3 carbons here. So we should have 3 carbons here as well. So went from anhydride to an ester. Pretty simple. But now the question is, let's say we have another alcohol group, but this time it has 2 alcohols. Which of these 2 is going to add on to the anhydride to make an ester? So let's first look at the differences between these 2 alcohols to determine which one is going to be added on. And let's first draw what each one would look like. So this we'll call A. If we add on oxygen A, and I should probably number, that'd be helpful. If we add on oxygen A, then that would give us this product. Or if we added on oxygen, let's call this B, then let's show the product of what that would be. So this is B. Then that's going to be attached. It's going to be like this. And 2, 3, 1. So we have 2 possible products. We have to decide which one it's going to be. And it's actually not, the answer isn't too difficult. It's one of the most common answers you've heard in organic chemistry. How do you decide which of these 2 is going to be added on? Well, how substituted is oxygen A? Alcohol A. Alcohol A is attached to a primary carbon. So that is a primary alcohol, where oxygen B is attached to a secondary carbon. So that is a secondary alcohol. What's the significance of saying whether it's a primary or secondary alcohol? Well, one of the most common answers in organic chemistry has to do with sterics. Which one is least sterically hindered? And that is going to be the primary alcohol because it's attached to a primary carbon. So there's less stuff around it. There's hydrogens here. As opposed to the secondary alcohol, which is attached to a secondary carbon that has 2 other carbons around it. So this secondary alcohol is more sterically hindered, and this primary alcohol is less sterically hindered. So it's going to be the less sterically hindered alcohol that adds on to create the ester. So it's going to be oxygen A, or let me write alcohol A. Alcohol A because it is less sterically hindered. So that is why alcohol A is going to be added as opposed to alcohol B. And this is important because a lot of times if you have a dialcohol group, you can use an anhydride to protect as a protecting group for the least sterically hindered oxygen. So that's why that reaction is important. The anhydride is going to react with the less sterically hindered alcohol, and that's usually used to act as a protecting group. So that's going to be that answer. Oh, let me go to the 3. And let's go to the next one. This reaction is called transesterification, and that just means you're going from one ester to another. And this reaction is in equilibrium. And I asked, what principle does that remind you of? Anytime you hear equilibrium, the principle you should be thinking of is Le Chatelier principle. That's the principle you should always think of when you hear equilibrium. So we need to determine what we could do in order to make sure that we only have this product and that it doesn't convert back to the starting material. And according to Le Chatelier's principle, if you add one of the reagents on one side in excess, then that's going to drive the reaction more towards the opposite side. Because if you have a whole bunch of these alcohols to react with few starting materials, anytime this ester converts back to this ester, because there is so many of this alcohol, it's going to react right away and push it back to the other ester. So the first thing you can do is have excess of that alcohol. Or the other thing you can do is kind of the opposite, is take away this other alcohol. Because if you take away, and really the process is distillation. If you distill or take away this other reagent on this side, then that means that once this ester is created, if you've taken a lot of this away, then that means there is nothing for this ester to react with in order to convert back to that ester. So those are the two things you can do. You can either make this alcohol in excess, so anytime this ester does go back to the ester on the left side, because there's so much of this alcohol, it's just going to react right away and push it back to that ester. Or you can take away this alcohol as it's being created. So then when this ester is formed, there is no alcohol to react with in order to push it back to that ester. So that's the two things you can do. And let me know if you have any questions on any part of the SI sheet.